I'm dealing with an operand. Which again is a non-zero positive specific value. Is my new computer blocking the... Just let me know if my new computer needs to be moved. So what's the conclusion? It's divergent because as long as we get to that specific, unique, positive value, then whatever we compare it to is a good comparison. Meaning the behavior of this is going to mimic the behavior of this. So, I'll do therefore. You doing okay with these? Please don't fall into the trap. It's very common. I'll say, here's a problem. Try one of these tests, and so immediately a student just starts taking the limit. Okay, if you take the limit, you got to tell me which test you're using. I can't tell you how common that is. Some of these use a limit, some of them don't. The geometric series does not use a limit. Neither does telescoping. Test for divergence does. Yeah.
So for this one, if it was on test, would it have to say compared to the limit comparison? Or?
So the test used is limit comparison in this case. Yeah. Can I give you another one? Let's try another one. Oh, by the way, you can't use either comparison test on this. Just because. You have to use a different test in this case. So please use a non-comparison test for this one. What test can I use? What's that? Can't use p-series. P-series is 1 over n to a constant.
Can you use integral?
Hey, I can... It's not okay. What test am I going to use? Integral test. There are 3 conditions you have to satisfy for the integral test. What's that?
Positive.
Continuous, decreasing, and you need to prove that it's decreasing. So take your time, walk through each piece. Then you will have permission to use the integral test. This is the most important step. We've got to change it from a discrete function to a continuous function. Otherwise, one of those three axioms will not apply. Yes, you got to use quotient rule. I know. How do we prove that it's decreasing again? I forgot. Derivative. And when I do the derivative, what am I looking for? Negative. It's always going to be negative after a certain point. Looking a little suspect. We want to know when it's negative, right? The denominator is always positive, not an issue, right? Even if we had negative values for x, which we don't, we're still squaring it. So it's always positive. So I basically need to know when this is true. This is where you have to get you have to compare the different regions in between the critical values and all that. You're a pre-calc teacher. Hopefully went through this. I don't want to hear any comments. I'm sure I went through this. Let's pick a number that's less than 0. Let's pick -1. -1 cubed is -1, right? -1 minus -1, that's going to make that plus, right? So that's positive. How about here? That's negative as well. This is a negative region. Let's pick a number between 0 and 2. Let's pick 1. Keep it simple, right? So 1, that's positive. We're good. 1 here is going to make this 2 minus 1, which is 1. That makes it positive there. Oh no. So let's say that x equals 10 now. I'm out here. X equals 10. 10 is a positive value, we're good there. 10 here, this is going to be 2 minus 1,000, right? So that's for sure negative. So we're good. As long as it's bigger than 2. Remember, even though it starts at 1, that's okay. We can have one piece that's going to make it a little uncomfortable, but after 2, we're good. So it's decreasing. At 2, we get.
Wouldn't be cubed too? Like the cube root too? Because
No, anything 2 plus.
Oh, yeah.
no, it will be cube root too.
Yeah, it would be. Sorry, that's always right. Doesn't work anyway. Root of 2 is still bigger than 1. So, here we can. Thank you. So basically, we've satisfied that last option. We really do need to look into it, though. So what's our conclusion? We're now allowed to use the integral test. That's our conclusion. Okay. I was picking these problems out. I wanted one that was going to really have to sort of bring us back a little bit and kind of remind us how to integrate and all that kind of stuff. So. I got a couple of options here on integrating this. I could do partial fraction decomposition because that denominator factors. However, a simple substitution should suffice. You have to fix the boundaries. No, hang on. Yeah. So when x equals 1, I'm going to get 1 plus 1, which is where the 2 comes from. Because these are now u boundaries, right? Now when x equals t, like it does here, I'm going to get t cubed plus 1. see why I try to avoid the integral test. It's taking time. What's happening here as t goes to infinity? For sure goes up to infinity, right? In fact, it goes up to infinity even faster than if it was just t.
So when do we figure out why we're doing all this?
Say it again?
When do we figure out why we're doing all this?
Later. Yeah, it's coming. So what's going to happen is we're going to start doing the actual power series building, which is what ultimately we're getting to. And part of the power series is we're going to have to go, is this convergent or divergent over here? It is, okay, so we can move on, type thing. So we're going to have to just quickly run one of these tests. Now this one isn't quickly. Any questions? Would you please redo this problem, but this time use the limit comparison test? Remember the original problem's up there.